Hey everybody, welcome to 3.2. We are going to look at graphing rational functions and also specifically adding the slant asymptotes to the graphs as needed. So we'll explore the slant asymptotes of rational functions in order to sketch those graphs. So we want to find all the information for the equation shown here. So this is kind of a review of what we did from lesson 3.1. We want to factor. So to factor that numerator, we need factors of 9 that add up to 6. That's 3 and 3. So x plus 3 times x plus 3. Over x squared minus 4 is a difference of squares. So x plus 2 times x minus 2 is how that will factor. Now, we do have a factor squared in that numerator, x plus 3 all squared over x plus 2 times x minus 2. And that is simplified factored form. And we'll be coming back to that a few times. In terms of wholes, this graph does not have one. There are no factors that divide out, so there are no wholes. For the roots, we set the numerator equal to 0. So that's x plus 3 squared equaling 0. So x plus 3 equals 0 and x equals 3. A root is a point, so that's 3, 0. We can plot that on the graph. Now, that is multiplicity. That's if a factor is squared. So, yes, there is multiplicity here. This is a double root. That's going to make it a tangent root or a bounce, the tangent bounce. And that is going to be a tangent bounce at 3, 0. Now, for asymptotes, we set the denominator equal to 0. So there's 2 factors in that denominator. X plus 2 equal to 0 and x minus 2 equal to 0. So those asymptotes are at x equals negative 2 and x equals 2. So we'll go ahead and graph those as dashed lines on the graph. To do the end behavior, we compare the degrees of the numerator and the denominator. So the degree in the numerator is 2. The degree in the denominator is also 2. So these are the same. When the degrees are the same, we play the coefficient game. The coefficients, the leading coefficients of those factors, of those terms, are both 1. So that means we have y equals 1 over 1, or a horizontal asymptote at y equals 1. So I'm drawing that horizontal line at y equals 1. And again, it is an asymptote, so it is dashed. To find a y-intercept, that is always where x is equivalent to 0. I would use the unfactored form. For this, it'll be a little simpler. When x is 0, y would be 9 over negative 4. All the other terms turn into zeros. So that y-intercept is 0, negative 9 over 4. Now, negative 9 over 4 is a little past 2. So y-intercept a little past negative 2. I don't have to be too precise here, but that's where it is. Now, as far as the domain of this graph goes, domains break at wholes and vertical asymptotes. So this domain will break at our 2 vertical asymptotes. So from negative infinity to negative 2, from negative 2 to positive 2, from 2 to infinity would be the domain in interval notation. In set notation, x such that x cannot equal negative 2 and positive 2. Don't forget to put that in the curvy braces. Now, that is all the relevant information, all the pertinent information we would need in order to graph this. All we have are some asymptotes and 2 points. And that really is enough to graph this. I'm going to start in this middle section because we have that y-intercept. We know that the graph does not cross the x-axis anywhere except 3, 0. So this section in the middle between the two vertical asymptotes does not have a root. So from the vertical asymptote, from the y-intercept, this graph basically has to go down. It can't go a different direction. It can't go up because it will cross the x-axis. And there is not a root in this center section of the graph. Now, from here, use the tangent and together ideas. We look to see if there is a tangent. So I'm looking at this vertical asymptote at x equals -2. It is not a tangent. So the right side of that vertical asymptote went down. The left side will have to go up because it's not a together. We can't cross a vertical asymptote, and the ends of the graph will approach a horizontal. There's not a root on the right side of this graph, so we never cross that x-axis. Now, in terms of the far right side, we have a similar idea with the vertical asymptotes, left side, right side, left side, right side. The left side of x equals 2 goes down, so the right side has to go up. There's not a together, so the two sides of the vertical asymptote have to go opposite directions. Now, this is a little unusual, a little weird, in that we do have to touch this at this root. Okay? We know from previously that this is a tangent root, so it will bounce. This is a tangent root, so it will bounce. Okay, so we're going to come up from high. We're going to hit that root. We are going to bounce back, but we also have this horizontal asymptote to contend with. So we're going to bounce off that root, but we're not going to bounce up very high because we have to approach that horizontal asymptote on the end of the graph. It is okay that our graph crossed that horizontal asymptote in the middle. Not the middle section, but it's okay to cross a horizontal asymptote as long as it doesn't happen on the far ends of the graph, and that's what we have here. So let's review a little bit about the end behavior rules. We had a little math poetry that went with this. Low over high, 0 equals y, meaning there is a horizontal asymptote at y equals 0. High over low, slant we go, meaning there is a slant asymptote for that graph. When the degrees are the same, we play the coefficient game, meaning a horizontal asymptote at y equals a over b. That a and b are the lead coefficients. That really means to divide the lead coefficients, just like we did in the problem above. Now, what's a little new are slant asymptotes and how to find them. It's going to be a primary focus of today's lesson. Slant asymptotes may also be called oblique asymptotes. Those are the same thing. They occur when, trying to drop this thing. They occur when the degree of the numerator is greater than the degree of the denominator. They occur when we have a high over low. They occur when we have a high over low. That is a slant asymptote, also known as an oblique asymptote. To find the equation of that line, which is what we need to do, we will divide the numerator by the denominator. Divide, meaning we'll use synthetic division. The result of that will be a linear function that represents the slant or oblique asymptote. So let's take a look at how that works. Example 1A, we have this rational function. We want to find just the end behavior. To look at the end behavior, we compare the degrees. The top has a degree of 2. The bottom has a degree of 1. So that is a high over low, which is a slant and or oblique asymptote. Okay. Now, to do this, we use synthetic division. Across the top, we put the coefficients of the numerator, 1, 1, negative 2. On the outside, we're going to put a 1. It comes from this number, and it does change sign. Don't forget to change that sign. Now, when we find that asymptote, we bring to divide, to do the synthetic division, we bring down the 1. Multiply, 1 times 1 is 1. Add, we get 2. Multiply 1 times 2 is 2. Add, we get 0. This 0 is the remainder. 2 is the constant. 1 is the x. So the answer to this division is x plus 2. Now, this is an asymptote. It's the equation of a line on the graph. That line is y equals x plus 2. Y equals x plus 2 is the slant asymptote. That is the asymptote the graph will approach on the ends. So let's try part B. Again, we're finding just the end behavior. So we look at the degree. The degree on top is 2. Degree on bottom is 1. That is a high over low. So that is a slant or oblique asymptote. Okay, to find it, we use synthetic division. 1, negative 9, 14 on the inside. 3, yes, that changed signs on the outside. Bring down the first coefficient 1, times 3 is 3. Add, we get negative 6. Multiply by 3, that's negative 18. Add, that's negative 4. Negative 4 is the remainder. Negative 6 is the constant. 1 is the coefficient of x. Now, there's a little rule here that applies. There's a little rule here that applies, and that is for slant or oblique asymptotes. We ignore the remainder. We ignore the remainder for those slant oblique asymptotes. So, just disregard it. X minus 6 is the result of that division. Y equals x minus 6 is that slant asymptote. So the line y equals x minus 6 is what our graph will approach on the far ends. So let's try putting all of this together. And let's look at example 2. Example 2, we need to factor the numerator to start with, as always. So when we factor that numerator, we notice we have cubes. We have x cubed plus 3 cubed. So that rule for factoring cubes says that a cubed plus b cubed factors as a plus b times a squared minus ab plus b squared. That is your factoring formula. That's a b for sum of cubes. So as we plug things in, our x is the a value. The 3 is the b value, not 27, but 3. Take the cube root of each of those to do the factors. So this factors as x plus 3 times x squared minus 3x plus 9. There's our factored numerator. The denominator is the difference of squares, x squared minus 9. Both of those values are perfect squares. So to factor, take the square root of each, x plus 3 times x minus 3. And that denominator is now factored. Now, if you look at this and notice, hey, there's something there the same, you're right. That x plus 3 divides out. So simplified factored form here is x squared minus 3x plus 9 over x minus 3. And this is simplified factored form. We're going to be needing this, so I'm putting a big box around it now. Now, let's find all the pieces. We do have a whole. We have a whole because a factor here divided out. So to find that x value, take that factor x plus 3, set it equal to 0. That x would equal negative 3. So the x coordinate of that whole is negative 3. To find the y coordinate of that whole, we plug the negative 3 we just got into this simplified form. So negative 3 squared minus 3 times negative 3 plus 9 all over negative 3 minus 3. So if we work on that a little bit, negative 3 squared is 9. Minus 3 is plus 9. And then there was already a plus 9 over negative 6. So this is 27 over negative 6, which dividing by 3 reduces to negative 9 over 2. So the whole here is at negative 3, negative 9 over 2. We took the factor that divided out, set it equal to 0 to find the x. We plugged that x into the simplified factored form in order to find the y. Plugged it in, worked it out, reduced the fraction. So negative 3, negative 9 over 2 is where there was a hole in this graph. Negative 9 over 2 is negative 4.5. So negative 3, negative 4.5, and here's our hole. Now, to find the roots, we need to set the numerator equal to 0 in order to solve that. I'm going to come down here under the graph and find those roots. So x squared minus 3x plus 9 is equal to 0. This will not factor any further. There are no factors of 9 that add up to negative 3. We cannot find numbers that have a product of 9 and a sum of negative 3. So what we have to do here is use the quadratic formula. A is 1, B is negative 3, C is 9. Plugging that in, x equals negative b, so positive 3, plus or minus square root of negative 3 squared minus 4 times 1 times 9, all of it divided by 2 times 1. Just plugging into the quadratic formula. Now, simplifying this, 3 plus or minus the square root of something all over 2. Negative 3 all squared is 9. 4 times 9 is 36. 9 minus 36 is negative 27. So we can actually stop right here because the purpose of using the quadratic formula was to find the roots, the zeros, the x-intercepts. This is not real. This is non-real. So what that actually means is that our graph will not cross the x-axis. There are no roots here. Our graph will not touch or cross the x-axis in any way. So we don't have to simplify that root any further. We know it's not real. We're good. So let's find some asymptotes. Vertical asymptotes occur when the denominator equals 0. So x minus 3 equals 0 means that x equals 3 is a vertical asymptote. So we will draw a vertical line at x equals 3. A tangent or together would occur if one or more factors were squared. In the simplified form, There are no factors that are squared, so there's no tangent or together. That x squared on top is a term. It's not a factor. It's not multiplied by everything else. It's not a factor. It doesn't make a tangent or a together. Now, end behavior. In behavior, we compare the degrees. In behavior, we compare the degrees. We have a degree of 3 in the numerator. We had a degree of 2 in the denominator. I tend to use the original equations before we messed with them. It's a little bit easier to see those powers there. So this is a high over low, which does make it a slant or oblique asymptote. So to find it, we need to do the synthetic division. So we're going to divide out. We had 1, -3, 9. We're dividing that by x minus 3. So we put that positive 3 on the outside. Bring down that first 1. 1 times 1 is 3. Add, we get 0. Multiply, we get 0. Add, we get 9. 9 is the remainder, which we'll disregard. 0 is the constant. 1 is the x, or the x coefficient. So y equals x plus 0, or just y equals x is our end behavior. So that is a slant or oblique asymptote, and we need to graph that equation. Y equals x, easiest equation to graph ever. Y-intercept is at 0, 0. Slope is 1 over 1. Up 1, right 1. Over and over again. Down 1, left 1. Over and over again. And there is our slant asymptote. Remember, an asymptote's not really part of the graph, so we're going to leave it dashed. It's a boundary line. It's not really a point on the graph. Now, to find the y-intercept happens when x equals 0. So when x equals 0, plug that in. I would use original unfactored form because everything with an x zeroes out. 0 to the third is 0 plus 27. 27 is our numerator. X squared minus 9. 0 squared minus 9 is just -9. So that's -3. That y-intercept is 0, -3. And here's our graph. There's the y-intercept. Now, to sketch the graph, we really do have enough information. Remember, we can never cross vertical asymptotes. We need to approach the horizontal or slant asymptotes, and we can only cross the x-axis at designated roots. We have no designated roots, so there is no crossing this x-axis. We do know that the y-intercept and this hole, being in the same section, need to connect. From the hole to the left, that's in behavior, we'll need to approach that slant asymptote. From the y-intercept to the right, we have to approach that vertical asymptote. We can't cross the x-axis, so we can't go up and over. We have to go down towards that vertical asymptote. Now, if we think left side, right side, top and bottom, the left side of that vertical asymptote went down. There's not a together, so that right side has to go up. We also have to approach the slant asymptote on that piece. So we have a little V sideways check mark U-shaped thingy that connects over here. And this is your graph. Its domain gets broken up by holes at -3 and at vertical asymptotes at +3. So -infinity to the hole at -3, then -3 the hole to the vertical asymptote 3, then from that vertical asymptote to infinity. If we were to write that in set notation, it's x such that x cannot equal ±3. So here's your function. Let's try another one. Let's look at example 3. Now, this one's going to be a little more involved in the factoring. It's still very, very doable. The numerator here has 4 terms. So to factor 4 terms, we need to group in greatest common. First group's greatest common is x squared. Factor that out. We have x plus 4. Second group's greatest common is minus 1. Factor that out. We have x plus 4. Watch that negative dividing out. Then x squared minus 1 is one of the factors. X plus 4 is another. Now, before we get too carried away, that x squared minus 1 will factor further. Yeah, it really will. It's a difference of squares. So x squared minus 1 factors into x plus 1 times x minus 1. And this factor x plus 4 is still there. So that entire numerator is x plus 1 times x minus 1 times x plus 4. Then we need to divide that by, we need to factor that denominator. We would need a product of negative 12 and a sum of 1 in order to factor that. That's a negative 3 and a positive 4. Because of the 1 coefficient here on the bottom, we can just say x minus 3 times x plus 4. Now, if we notice, we do have a divide out here. X plus 4 divides out. So our factored simplified form would be x plus 1 times x minus 1 over x minus 3. This is simplified factored form. Now, because we had a factor divide out, we do have a whole. X plus 4 equals 0. X equals negative 4. Is that y-intercept? Is that x coordinate? To find the y value, plug that negative 4 in for x in the simplified factored form. So negative 4 plus 1 times negative 4 minus 1 over negative 4 minus 3. So that's negative 3 times negative 5 over negative 7, which is 15 over 7, and it's negative. So negative 15 over 7 is the y-coordinate of the whole. Now, to graph that, negative 15 over 7 is a little bit more than 2. Negative 14 over 7 would be exactly 2, so it's a little more than that. So go to your x, negative 4, go a little past negative 2, and here's our whole. Now, to find the roots, we want to set the numerator equal to 0. That will be x plus 1 equals 0. X minus 1 equals 0. So those roots would be negative 1, 0, and 1, 0. Remember to write those as points because they are points on the graph. Go ahead and plot those points as soon as you find them. Let's look at asymptotes. Asymptotes are when the denominator is equal to 0. So x minus 3 equals 0, meaning x would equal 3. An asymptote is a line, so the equation of a line would be x equals 3. Graph that vertical asymptote as we find it. In a tangent together, there is none here because there is no factor that is squared in factored form. This factored form right here has no factor squared, so there is no tangent or together on this graph. For end behavior, we want to look at the degree. We have a degree of 3 on top, degree of 2 on bottom. That's a high over low, which means it is going to be a slant or an oblique asymptote. So to find it, we need to use synthetic division. Now, the problem is we have x plus 1 times x minus 1 on top over that x minus 3. We need to multiply x plus 1 times x minus 1 back together in order to get it in a form where we can use synthetic division. So multiplying this back together, we end up with x squared minus 1 over x minus 3. So to do the synthetic division, we need the 1. We need a 0 because we skipped a single x term, then the minus 1. Put the 3 on the outside, that changed signs. Bring down the 1, times 3 is 3, add we get 3, times 3 is 9, add we get 8. That 8 is the remainder that we'll leave alone. 3 is a constant, 1 is the coefficient of x. So the equation of this end behavior is y equals x plus 3. Y equals x plus 3 is going to be that slant asymptote. We had to multiply the factors back together, and then we could use synthetic division. So y equaling x plus 3, start at 3 on the y-axis, and that's a slope of 1, up 1, right 1, as many times as it will fit on the graph. And then down 1, left 1, as many times as it will fit on the graph. And there's our slant asymptote. Now, for the y-intercept, I'm going to come over here and find that. Y-intercept is always when x is equal to 0. Plug 0 in for x. We get, was that negative 4? Negative 4 on top over negative 12 on bottom. So that's 1/3. So that y-intercept is 0, 1/3. So just a little bit above the x-axis on the y-axis. And there's our points. There's our points. Now, this piece of the graph puts together pretty nicely. Okay, we can see a lot of points here. We know that the root, the y-intercept, and the other root need to connect. They'll need to go towards the hole, not include the hole, and then go towards that slant asymptote. Then we're already heading back down. We need to go down, 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 down as we approach the vertical asymptote there. These points back on where you can see them. Okay, so there is a piece of this graph. Now, at the vertical asymptote, left, right. On the left side, we went down. On the right side, there is not a together, so it has to go up. So we have that little curve, little funky curve in that top section. We know it's supposed to be there because any x value that's not a whole or vertical asymptote needs to be included. So all the x values on this side do need to be included, and that is where the graph goes. So the domain of this graph, the domain of any of these graphs, gets split up by holes and vertical asymptotes. So negative infinity to the hole at negative 4, then negative 4 to the vertical asymptote at 3, then 3 to infinity. And there is your domain. If that were in set notation, we curvy braces x such that x cannot equal negative 4 and positive 3. That would be set notation. So there's your graph. The other two examples are going to be on a separate video for time and size and uploading space. So I'll be right back with the other one. See y'all in just a minute.